Okay, we're going to begin our discussion of Chapter 2 in Section 2.1, where we discuss Cartesian coordinate systems. Rectangular coordinate systems are, Cartesian are a subset of rectangular coordinate systems, and essentially what we're talking about are grid systems that we're going to use for mapping. Now, you're all probably familiar with grid systems used as mapping tools. Here's a grid system where you have essentially a grid of perpendicular lines superimposed over a picture of something. And in this case, we have lines superimposed over a park here, the Silverwood Park. And you can see that some of the lines run horizontal and other lines run vertical. And the way the grid system works is, suppose you want to meet up with somebody at a crossroads here. Say you want to meet up with somebody in this location at this crossroads. So you get on your cell phone and you say, hey, we're at, so you look at the D location here, you come up. So we're at, looks like D, half of D and E, but let's just pick D. We're at D4, the intersection at D4. So that'll get you right to there. So if you wanted to have a picnic on the side of the water here by the roller coaster, you might say, okay, we're gonna bring all our food to M6 and let's meet up there. We'll decide if it's a good place for a picnic or not. Maybe there's some picnic tables there, maybe not. So that's how grid systems are used for mapping. Well, we can do the same thing with real number lines. Say we have a real number line here that's horizontal. Starts at 0, count up through 1, 2, 3, and maybe we can go all the way to infinity here, and then we can go the negative direction too, so on and so forth, out to negative infinity. We could then draw another number line perpendicular to this, and we can number it from the place where it crosses that we call the origin. So and number it upwards, positive. This is just a convention, arbitrary convention we decided on. We could have done this in the opposite direction, and maybe some people do, like maybe in Russia they do it opposite. Sometimes the Russians do everything backwards, just to be different. No, I don't know why they do it backwards, but yeah, we use the right-hand rule when we're talking about positive rotation, and they use the left-hand rule. But anyways, getting back to topic here. So this again is a real number line, and this one is vertical. And these two are perpendicular. There's 90 degrees between them. Perpendicular. And essentially they cut space up into 4 quadrants. So quadrant 1, and this is how we've arbitrarily decided to call these quadrants. That's quadrant 2, quadrant 3 is down here, and quadrant 4. A fellow by the name of René Descartes he formalized this idea of 2 perpendicular real axes, and he decided, let's call this y, the y-axis, the orange one the y-axis, and let's call the blue one the x-axis. So we started using that approach, and as the story goes, he was quite the carouser. He would stay out late at night drinking and carousing, and I guess womanizing, though I'm not sure about that. And So he'd get back to his place of residence in the wee hours of the morning and then fall asleep and sleep all morning, and people would call him lazy for sleeping all day, and he'd say, no, I'm not lazy. I lie in bed and I think about things. And one of the things he was thinking about one morning, supposedly, as he was lying in bed, was that, hey, there's this fly crawling around on his ceiling. And he recognized that using two perpendicular axis systems like this, he could perfectly map where that fly was using the distances on both axes. So for example, the fly was 3 units in the x direction and 2 units in the y direction. And when we find points in this sort of axis system, we call this an ordered pair. Ordered pair. Because there's always an x point and a y point. Well, because of the work he did in this area, we named it after him, we call it the Cartesian axis. And it's a rectangular axis system. So we could find points in any quadrant. For example, if I were to find this point here, it might be the point -1 in the x direction, 1 in the y direction. So that would nail that point down. We don't have to only use integers. We could use fractions or decimals even. So maybe this point here is 3/2 in the x direction, and we're heading down in the minus direction here, -2.5, so I use a decimal and a fraction here. That's okay, we're allowed to do that in the y direction. So these are ordered pairs, and this is how this works. So now we have the ability to map things on a flat space, and we have the ability to combine both algebra and geometry into one science now. So just as a last point, where these two cross here, the origin is the point 0, 0. Now we can use this approach to actually graph equations. So I have an equation here, y equals 2x plus 1. Let's make a table of the values of this equation. So I have x values and I have y values. Let's make a table of x and y values and get some point pairs that we can plot on this to see what this equation looks like when we plot it over here. So let's begin. So when x is 0, y is 2 times 0 plus 1 equals 1. When x is 1, y is 2 times 1 plus 1, that's 2 plus 1 is 3. Do one more in the positive. When x is 2, y is 2 times 2 plus 1 equals 5. Okay, and we also may as well go in the negative direction. -1, when x is -1, y is 2 times -1 plus 1 is -2 plus 1, or -1. And we'll do one more point. X is -2. So 2 times -2 is -4 plus 1 is -3. So if I plot these points, x is 0, y is 1, x is 1, y is 3, x is 2, y is 5. Guess we need a couple more tick points up here. X is 2, y is 5. And then let's go, x is -1. So got to go to the -1 here. y is minus 1, x is minus 2, y is minus 3. Notice all these points fall on a line, and that's because this is an equation of a line. It's no surprise that that happens. Now we could use this equation to do a number of things. One of the first things we're going to try to do is let's try to find the intercepts, the places where this crosses the x-axis. That's the x-intercept, and the place where it crosses the y-axis, which is the y-intercept. And anytime you cross the x-axis, anytime your plot ever crosses the x-axis, one condition always occurs. It always does that when the y value equals 0. So every time this happens, y equals 0. And if that's the case, well, we can solve for this point by setting y equal to 0. So y equals 0, and solve our equation for the x value that is. So now we have 2x equals 1, or x equals 1/2. So this is the x-intercept. And that makes sense. This looks like, if I drew this exactly correct, it would be exactly right. But this looks like the point 1/2 and y0 at that point. 1/2, 0, that's the x-intercept. So x equals 0. Of course, y is equal to 0 because that's what we set it as. Okay, well, now we can do the same thing to find what our y-intercept is. And you can look at the plot, and it actually kind of sticks out on the plot. But here we want to set, whenever our plot crosses the y-axis, as you can see, the value of x is always 0 here. So the same idea as before, except now we have x equals 0. So now we're going to change our equation up just a little bit to do this. We're going to say y equals 2 times 0 minus 1. And this just falls out directly. 2 times 0 is 0. So y equals minus 1. So y equals minus 1. This is our y-intercept. And notice, that's b in our line equation. That's our y-intercept in our point, or our slope-intercept form of the equation for a line. So yeah, that makes perfect sense there. But sometimes the equations we're going to use are going to be more complicated than just these linear equations. And we'll use the same process. When we're looking for an x-intercept, we'll set the equation we'll set y equal to 0, and we'll solve for x. Sometimes there's multiple x's for the intercept. And for the y-intercept, we're going to set the equation, we're going to set x equals 0 in our equation and solve for y. Okay, that's all I'm going to do here. Come back.